Hello, everyone. So there are two things you should know about me. The first one is that I work in Canonical, as you might have guessed from the presentation template, but I work in a team called Office of the CTO. So we get to work on a bunch of cool projects at the same time, right? We do DQLite, Chisel, SQLair, a bunch of secret projects. And the cool thing is that then those small projects, they get used in a bunch of products. But they also have another thing in common, and that is that they are all developed using Git. And we are a remote company, so that means that everything, most of the discussions, happen using Git, either in GitHub, either in PR comments, or either by sharing branches or things like that. So that leads me to the second thing that you should know about myself. And that is that I don't know when, but at some point I became a little bit obsessed with Git. I used to just use like the VS Code UI or whatever, just click the pull commits, do my commits locally, and then push them. But at some point, maybe because I had to work on several of these projects at the same time, and I had to do a lot of rebasing, I was just frustrated. Every time I needed to do something, I had to copy the whole directory, I had to do the operations, and then I had to pray that everything worked. I had to check the files manually, and then if there was a conflict or something, I had to copy the data back in. And that happened to me a lot of times. So at some point, I just said, OK, I'm going to learn more about it. And I think that this frustration is perfectly summarized in this comic, in this XKCD. Basically, a developer is saying that Git is super cool, right? Because it has a distributed graph theory tree model, a mouthful. And then the other person asks the developer, OK, that's super cool, but how do we actually use it? And the answer is, I have no idea. Just memorize a bunch of commands, just use them, and if you get any errors, just copy your directory back in. And that was my experience, and I think a lot of people also work in this way. Every time you have to delete a branch or do a rebase or something like that, you are just scared that all the progress is going to be lost. So that's my promise for this talk. We are going to learn the data that Git actually stores every time you do an operation, and we are going to go into some depth in order to know how it's actually represented on disk. And the idea is that you will develop an intuition for what operations are going to be destructive and which ones are not. And disclaimer, rebasing is not destructive, deleting a branch is not destructive. Essentially, nothing is destructive. And I hope that, well, I'm sure that after this talk, then you will not copy the directory to have a backup and then again, or check the files manually to see that the operation that you were doing actually worked. And instead of showing you some graphs of commits and some arrows and changing arrows in nodes, or instead of me telling you a bunch of commands and how you can go back just by typing this string syntax, I want to do this a little bit differently. I want to explore Git together. So we are going to do this by actually running some Git commands here on the terminal on the top right. I hope that you can see the text. Can you? OK. And then we are going to use the terminal on the left to tell us what files changed. So if Git creates a file inside the .git directory, basically it uses that directory to track all of the state, then a green line is going to appear with the file. If it deletes some file, then a red line is going to appear, and when it modifies a file, then a blue line is going to appear. So the idea is the following. I'm going to run a command, then we are going to look at the files and why they changed, and then we are going to look at the files themselves. And here at the bottom, I'm just going to have a terminal that looks at the graph in a very simple way so that you know every time we are doing a branch operation or something, which commit we are currently in, because it can be hard to track. So, OK. So let me show you an example. So for example, let's create the repository now with Git init. And we can see on the left here that there were a bunch of files being created, right? But most of them are just sample files for scripts, and we don't care about those. So if we just remove them, we can see that the script shows us in a red line that the file got removed. And if we modify a file, then it's going to appear in blue. Those are the only three colors. OK, so let's start by creating a text file with just an A. And then, so at this point, Git doesn't know about it. It's listed as untracked when we run git status. And by the way, I'm just going to try to use the basic commands. we are just going to add a few, like a couple more for something that will be pretty handy, but I'm going to explain those. So we are going to basically be running git add, git status, and git commit. So in this case, status is saying that the file is untracked. If we add it, then Git is going to know about it. And we can see here on the left that there were 2 files being created. The first one is the Git index, and we are going to talk about this in a sec. But the second one is actually the most important one. It's a file under the Git objects directory, and that is going to be the most important one for the whole presentation. And the cool idea that Git has is that instead of tracking files as the concept of a file, what it does is it uses hashes. If you notice, this thing looks like a hash, right? Like 78, 98, 19, 22. This looks like a hash in hexadecimal. This only has a subdirectory because of performance reasons, but you can think of this whole string as a hash. And in fact, there is a command in Git that you probably have never used and you will never use again to get the hash of a file that is called hash object, and you can see that it matches exactly what we see here, 78, 98, 19, 22, whatever. And the idea is that Git takes the contents of a file, and then it adds some metadata just to say that the file was added by the user. Then it gets the hash, and it stores the file under the Git objects directory, and it compresses the file, but at the end of the day, it's basically a hash of the contents, and the metadata is just a field saying that it was added by the user. And that has a couple of benefits. For starters, if we had a copy of the same file, and we add the copy, you can see here that there was only 1 file being created, and not 2, because it has the same content, so it has the same hash. That means that if you have a copy of a file in several directories, then it doesn't matter because the hash is going to be the same one. And the second benefit of this approach is that if you think about it, it's immutable by default. And we're going to talk about this later, but the cool idea is that by using hashes as file names, if you change the contents of the actual object, then the hash is going to change. So you cannot change things in place. But now, what is stored inside the object? So there is another Git command, and this is the last one, I promise, called cat file, and you can put here a hash, the hash that we saw above. And by using -p, you can print the contents of the object. And the contents are, as I just said, only the contents of the text file. So in this case, just a single A. There is another flag for printing the type. This is essentially printing the metadata, and it's saying that it is of type blob. So that means that it was added by the user. OK, now let's get to the other file, the Git index. So as you saw, when we copied the file and we added it again, there was no new hash because the contents were the same. But it has to record somewhere that Git now knows that there is a.txt and acopy.txt. And the only file that was modified was the Git index. So it has to be that one. And if we print it in hexadecimal, here, let's just make it bigger, we can see that it's keeping track of the file names, a.txt and acopy.txt. And then it's keeping track of the hash that we saw before, the 78, 98, 19, 22, and the correspondence with the file name. And it's exactly the same for a.txt. You can see here 78, 98, 19, 22, whatever. So every time you add a file, Git takes the contents, it stores the file under the hash, and then it has to store the correspondence between human readable name and the hash. And it uses the index for that. And it uses the index only because the changes are not committed. So if we run git status, it's saying that I have some changes that Git knows about that they are not yet committed. So let's create a commit here, a.txt and acopy.txt. And we can see that a lot of things happen here on the left. And on the graph below, we can see that there was 1 commit being created. So let's go over these files individually. This one, the Git index, I just explained that. It changed because now there are no objects that are not committed. There is something inside a folder called refs. So presumably that's a reference, because every time you do a commit, we have a notion of a graph, and we are changing some sort of pointer. And we are going to talk about it later. Then there is a logs. It's not important for now, because it just stores, every time you do an operation, it stores like a a line saying you move from this commit to this one because of this reason. We are going to talk about it later. And these are just for UX reasons. So the important thing, again, is the Git objects directory. Because there were 2 objects being created. What are those? So let's try to print the type. For the first one, 83DA8D. And we don't need to put the whole hash. And it's saying the file is of type commit, not blob. And if we print the second one, we can see that it is of type, it is of type 9DA3. Okay, so what is exactly an object of type commit? And why, coincidentally, the hash here and the hash here is exactly the same one that you can see in the Git log? One of the, one of the big mysteries about Git. So let's just print the file. And we can see here that the file, let me make it bigger, the file here at the bottom, the file here at the top, it has a pointer to a tree, it has some human readable tag, like tree, and it has a hash. Then it has the author, the committer, and then it has the commit message. But the important thing is that that tree tag, because, again, the important thing is the objects directory. So if everything is stored in the objects directory, as we are going to see, and everything uses the same principle for addressing files, so in this case a hash, then the representation is very simple, right? If you want to reference a file from the commit, you just have to put the hash there, because they are, well, a file or a tree or whatever, because they are all in the same directory. And what is a tree? Because a commit is supposed to be a snapshot of your data, right? So it has to store the files. If we print the tree, now 90DAC, we can see that it's basically that it has the mode, it has the type of the object, that is blob, in exactly the same way that we had the tree in the commit, and then it has a hash. This hash is the one that we saw earlier for a.txt, so this is just the hash of a.txt. And then for a copy, it has to store the same correspondence, the same hash and the file name for a copy. Here the mode. And the cool thing is that if we had another directory, it doesn't have to store the whole path, because it can just store a reference to a tree, to another tree. And if you think about the format, then it's going to be exactly the same. It's going to have the mode, then instead of blob, it's going to say tree, and then it's going to have a hash. So it's pretty uniform. So that's what happens when you commit, right? And you can think of commits as just plain objects inside the Git state, and they have references to trees. And trees are just a collection of correspondence between file names and hashes. And again, the hashes are the contents of the files. But this is a special commit, because it's the first one, so it doesn't have a parent. Here, the graph doesn't have any pointers. And one of the most difficult things about Git is the graph, right? Because we think, or at least I used to think, that it was stored in a complex data structure somewhere, and every time you do an operation like delete a branch or rebasing, it has to do something very complex and destructive with that, right? So let's now create a new file and check our assumption. I'm just going to add it in the same way. Then the hash, there was a new hash being created, and the Git index changed, just like we saw before. And then I'm going to create a new commit called b.txt. OK. And again, you can see that the hash here matches the hash of the commit being created, and this is the tree. Let's print it. Let's cut the file. And this is one of the next most important points in the presentation. The graph is represented as only a parent label and a hash of the other commit. So if you see here, the hash next to parent says 83DA8D, right? This is precisely the hash of the first commit we created. So there is no magical graph structure that needs to be maintained on the site or anything like that. The important thing is that the commit has a reference to the previous one by hash. And you can access the same directory to get the previous one. And then you can go to the parent. And that way you can build the whole graph. So the graph is nothing else than having a tag and a hash. And in the same way, representing files is having a tag, in this case tree, and a hash that you can use to access the tree. And then, again, another level of indirection. So now that we have some intuition for the graph, because it's just parent and hash, what is going to happen if we have something a little bit more complex? If we have a branch, I create a branch and then I merge it back to the main one. So it's going to have 2 edges instead of 1. Let's do that quickly. So I'm going to create a branch called my branch. You can see here that the only thing that changed is the reference that we are going to see later, and the logs. And again, this is just for UX reasons. This is not important. And then I'm going to create a file called C. A file called C, yeah. And then I'm going to add c.txt. Git commit add c.txt. OK. You can see that the graph changed. There is a new commit, 06D6, whatever. And there is the tree. So now let's go back to main. The graph is going to change because that commit is another branch. And then we are going to merge that branch. And here I'm going to use a flag called no fast forward because the branch is super simple. So Git is going to realize that it's just one commit, and instead of actually creating 2 nodes, it's going to just pick the commit. So if you had a real branch, then you wouldn't need any flags. So in this case, we are going to create a commit called merge branch, and these files here are just so that you can keep track of the merge, because if there is a conflict, then you can always merge abort. But again, this is not important. This is just for UX. And we created the commit successfully. And we see here that there is a merge commit, FE, and it has a node, an edge pointing to the add.c.txt that we created in the branch, and another one pointing to b.txt that we created earlier. If we have some intuition about what happened earlier, then we can already guess how the commit is going to look like, right? Because it is not going to be much simpler than the previous one. So instead of saying that the commit has one parent, it's just going to say that it has 2 parents. So it has 2 tags, one parent and, well, 2 exact same tags, and they have different hashes. And that is how you create the whole graph. So to summarize it, if you have a commit, if you know that you are in this commit, then you can always go to the parents. And you can recursively go to the parents of those commits. And that's how you build the whole graph. You don't need anything else. There is no extra information. There is no extra structure. It's all here, and it's all addressed in the same way. It's just a bunch of hashes, and you need to go to the same directory in order to retrieve the objects. OK. But there are several questions missing, right? Because as I just said, if we have one commit, so what is exactly a branch? What is the refs directory? If you think about it, Git has to know where to start, right? And that's what a branch is. It's just a human readable name for saying this branch starts at this commit. But then the commit has all the necessary information for the graph. So the branch is just a human readable pointer. And that is the next big revelation, because if we print the references directory, if we cut the file and we go for main, you can see that the branch is nothing else than just the commit hash of the commit that we are in, right? And if we now create another file and we commit it, git add git commit d.txt, then if we print the same file, you can see that the commit changed. And now it's pointing to 6426500. So a branch is just a pointer, and then you have all the necessary information. So as I was saying earlier, when I delete a branch, nothing is happening, because if you think about it, it's basically removing this file. And this file is just a hash. So if let's print the log for my branch. And we can see that there are 3 commits, right? Let me print it. One line. Oh. OK, doesn't matter. Git log, my branch. So there are 3 commits: add c.txt, add b.txt, and add a and a copy, right? Now let's delete the branch. What happened? We just removed the reference. Nothing else. So it's just a file being deleted. And the file contained only the content, the hash of the commit. So if I create a branch now, let's create checkout B to create the branch again. And now the only thing I have to do is take the hash of the previous commit and reset hard. Reset hard is another one of those commands that you think is going to destroy the world, right? If you have committed your files, and this is a big if, then the only thing that it's going to do is change the reference. So now the branch is exactly the same way that it was before, and we have not done anything. Because, again, the most important idea is that a commit has all the necessary information to build the graph and to recover all the files. And hashes, the commit, the object directory, is immutable by default. So every time we create something or we delete a branch or do things like that, we are not deleting objects. What we are doing is creating new objects and then changing references, because the new object can just point to the previous parent. And that happens, for example, let's say that I add a file here called big.txt. Let's go back to mainline. OK, let's say that I add the file, and then I see that there is a new object, right? And I can print the hash. OK, let's now change the object so that it has all Bs instead of As. And let's add it again. Did I delete anything? Because a year ago, I would panic just thinking that I had deleted the only file that I had added, and I should have committed, and I have lost all my work. But I see that no file got deleted here. And that's because the hash, if the contents change, the hash needs to change. And we don't delete objects by default. So I can just use git cat file and use the previous hash. And we can see here that the contents were saved. And this is so common, like deleting your commits or doing a rebase and then realizing that you didn't want to do it or anything, or all of those operations are so common that Git has some utility so that you don't have to copy around the hashes. Because it would be very unintuitive if every time I need to change something, I need to copy the hash and then change it and then realize that it's not the change that I wanted, so I need to copy the file back again. And every time we do something with the branch, with the commits, so if I go back to the previous commit now, if I reset hard and I go back to the previous one, the merge one, we can see that the only file that changed, apart from the pointer, is the logs. And if we print the logs file, we can see here that Git stores for us a bunch of lines telling us that we were in this commit and then we changed to the next one. And the message why we changed is basically because I committed. In this case, I committed the initial commit. In this case, I changed from this one to the next one because I added b.txt. You can see here that at some point I also did a reset. At some point I did a checkout. So going back to previous commit is so common that it is stored in the logs. But again, you wouldn't expect everyone to open the logs and then have to read all the information and then copy the commit. So there is another command called reflog that parses this file and then prints it in a human-readable way. So it's just printing the hash of the previous commit. So this is the hash of the current commit, and this is the hash of the previous one. The previous one, I mean, undoing one step, not the previous one in the graph. And this is undoing 2 steps, undoing 3 steps, undoing 4 steps, and so on. So that's why if you search in Google for how do I undo a git commit amend, how do I undo a git rebase, how do I do whatever, you will find that it has this cryptic syntax. It's basically git reset head with the one in curly braces, right? And nobody explains why this works. Because it seems magical in a way, right? Like it has to be built into Git, that Git has to store something to remember the previous commit and restore the graph or whatever. It's nothing like that. So the only thing that this is doing, this is a shorthand for the reflog. This is just taking the second line in the log and going back to the previous commit. And it works because the commits don't delete information. As long as you commit things, nothing gets deleted because the moment you are going to change a commit, you have to create a new object because the hash changes. And that's the most important idea. Again, So we can just go back to the previous one by saying git reset hard head with the curly braces. And again, this is a shorthand for the hash. And now we can see that we restore the whole state that we had. So these are the two most important ideas. Again, immutability and that nothing gets deleted. And then we have branches that are human readable pointers to some commits, because the commits have all the necessary information to build everything, right? There are a couple minor things left. So for example, how does Git know that we are in the main branch? Because it says it here on my terminal, and if you run git status, you can see that on branch main. So how does Git knows the branch that we are currently in? And it's as simple as you could think. So there is a saying in computer science, everything can be solved with another pointer, with another level of indirection. So that is exactly what is happening here. There is a file called githead, and it's saying that we are currently in a reference, and the reference is to our branch called main. If I went to my other branch, to my branch, the only thing that changes, apart from the logs, obviously, is the git head. So if I print it again, then it's going to say that we are tracking a reference to my branch instead. So it's just one more hoop. We have the branch, the human readable names and the tags and everything, and then those point to the commits, and we use another pointer to know which branch we are currently in. And I want to add a few disclaimers here because, as I said, you can restore most of the information, right? Because those are just pointers or hashes, and the objects are not deleted. But that is not always true. So the reflog doesn't have a limited capacity, and there are certain commands and configurations that will make you lose the reflog, some entries. But as long as you are committing often and you don't have to restore something from 1 month ago, then nothing should happen. And the other important thing is that when you upload something to a remote repository, then the objects are not uploaded. So not all the objects are uploaded. Because you may have, if you think about it, every time you do a git add or every time you do a commit, and even if you amend, then you're creating an object. So that means that you would push a lot of stuff into GitHub or whatever. So what Git does is that it only pushes the commits that can be reached, that are reachable from a branch. So the algorithm is super simple. You just take all the branches and tags, and then you just color the graph by following the parent pointers, just as we saw. You go to the commit, you find the parent pointer, and then you go to all the parent pointers. And those objects are the ones getting uploaded. So if you have some changes that you made locally, like a rebase, obviously you can restore them locally. You cannot push them to GitHub and then restore them. OK. And with that said, I hope that I have fulfilled my promise and that I will never see you again copying the whole directory and then rebasing and then copying it back again, because you can, after doing a rebase, you can just go back to the previous commit by doing a reset with the curly braces, and you know why it works. And a rebase isn't changing anything, right? Even though it's moving commits around, it cannot change anything, because the moment you change the commit, even if you are changing the parent, it has to change the hash. So it's storing a new one. So now, every time you do a rebase, you can just go back with one command. Or even look at the reflog and do it manually. And that was one of my promises. The second one was that we saw a little bit about the Git internals. We went to some depth to explain how the objects were created on disk. And I think there are several takeaways that apply not only to Git, but to software engineering in general, so I wanted to talk about those. The first one is that a simple data representation is easily extendable, right? And this is in the context of the objects that we just saw, because they were basically as if they were plain text files, right? We could read them in the terminal. We could just see that there was a label pointing to another commit, another hash. We can see that the hash is referenced in the object directory, and the rest of the stuff is just plain text, right? We could read them, and in the same way that we could read them, we could create a script to just do it for us. So you don't have to rely on Git. You could write a very, very simple script that just uncompresses the object, then looks at the file format, because the file format is super simple. If you can understand it, then a script can understand it. And when I say you, I mean a developer in general, because even though you might not develop a script, you can use a third-party tool that does a lot of a complex operation or a custom workflow, and that can easily be developed just by looking at the Git format. Okay, and the second one that is somewhat connected is that a uniform representation for all data is very powerful. And what I mean by this is that all the data was referenced by hashes. So you could look in the object directory to get the commit, to get the tree, and to get the blob. And that means that if we develop a tool for uncompressing those files and getting the metadata, like git cat file, then we can develop it once and use it for all the files. We don't have to develop 3 different tools, or effectively 3 different tools, because the graph is stored somewhere, the commit is stored somewhere else, they have a different compression algorithm, or whatever. And this also means that conceptually it's simpler, because you can just think about hashes in the same way for all of them. So you can just think about a hash like a way to address an object inside the directory. And this is also the last utility, is that if you develop a more advanced feature, let's say that you were developing some sort of compression, Git has something called pack files. So instead of putting all the objects and pushing them to the remote repository, or even doing it locally, if you have 2 objects that are essentially the same, but only one byte changes, then it's going to store the first object and the delta. So pack files may have been developed for blobs, because there is a common use case of having very big files. Okay, but because all the files are exactly addressed in the same way, the blobs, commits, and trees, then you get that feature for free. And that means that if you have 10,000 files and you change one in a commit, that means that the tree is going to be exactly the same minus 1 line. So you can use the exact same feature, pack files, and you can, by developing it once, you can compress everything, blobs, commits, and trees. And it's useful for more use cases than you can imagine. And if those takeaways are applicable in whatever you are developing, then that means that you could simplify the mental model quite a bit. With that said, are there any questions? I will take that as there was too much good information and there is need to process it.
Oh, oi. So thank you for the talk. It was very clarifying. I have a question about the, well, I always thought that Git actually stores the diffs of files, but I think you didn't cover all what diffs. Well, because we just created new files, of course. But are those hashes changed when changing a file, or how does it work?
So Git doesn't store diffs. It stores the whole contents of the file, right? As I was just saying. And if you were to change the contents, then it will just create a copy of the file in the objects directory, and it will create a new hash. But that would be that would not be very performant. So Git does store diffs using something called pack files. You can get a pack file by running, for example, git gc for garbage collect, and then it takes all the objects and put them into a pack file. Or when you git push, you are also doing that. By default, the whole content is stored. Only as a sort of optimization, it stores the deltas, but still the hash is the same. If you were to change something that is stored in the pack files, then you will need to create a new file, a new object, and that would have a new hash. And when you do git diff, I don't know if the question was more about the command, but when you do git diff, it just takes the whole thing and diffs it. It doesn't store the delta automatically so that you can diff it.
Okay, thank you.
Hi, thank you for the talk. I was thinking about this git reflog command. Is that something that also works, for instance, when you know, at some companies, you may have people that do a git push force in a PR, for instance, and then if something wrong happens, does git reflog also allows you to undo the push commits in that?
So it depends, right? Because the short answer is yes, but it depends on what you have locally. So obviously, git reflog, it's a log of the operations that you have done locally. So that means that if you have the latest commit locally, even if somebody force pushes, then you can obviously get the commit back because you have it. Even if you have resetted the branch to the remote one, you still have it. You can look at the ref log. But to answer your question in more depth, because that never happens, right? If somebody force pushes, then you don't have the commit locally. GitHub, for example, stores the previous commits for some time. So even though I said it's not uploading all the objects, it's uploading some of them. So if somebody force pushes, the previous commit is still stored in GitHub, and you can just download it. It's stored by the hash and everything. The only problem would be knowing the hash, and that depends on a bunch of things. But I don't know if I answered your question.
Yeah, thank you.
Any more question? Okay, so that's it. Thank you to the presenter.